much for the introduction. First of all, yes, I'm the one of the civil engineers here invited. Thank you for the invitation. I don't know why it's continuous going, so hopefully it will be continuous going. Oh, I'll just make some time. Okay, so first I will need to emphasize that collaboration with Faculty of Mechanical Engineering, Professor Segmak especially, and the Innovation Center from Belgrade. It was, I think it's more than, there is more than a decade that we are collaborating also with Simon here. So Faculty of Civil Engineering from Transylvania University has a good cooperation with our friends from Belgrade University. So thank you very much again for inviting me. So I will present the structural integrity assessment part of a sustainable development. I will try to underline why structural integrity is considered as a sustainable approach, let's say in the civil engineering, and why we should care about. We'll see then to assess structures, why we need to assess structures. So first of all, I will present a very short introduction with some elements regarding sustainability, some cases of damages, especially for bridges, and then two study cases where I will underline the algorithm that I will be presenting, and in the end, some conclusions and further research. So, as the definition of the sustainable development given by the United Nations report from 1987 was like sustainable development is an approach to growth and human development that aims to meet the needs of the present without compromising the ability of future generations to meet their own needs. So it's very important to understand that, okay, we need to have this sustainable approach, taking into account three elements. So again, it's I think it's I know what is our control. So we'll need to control. So you need to have the environment aspect, the economic, and the social aspects together, put in one sustainable, let's say development. Some of the researchers will consider that sustainable development is an oxymoron. Like it's not sustainable. Any development is not sustainable because of the fact that any development should not be sustainable. So it cannot be sustainable. But again, I will emphasize why we need to do this approach in civil engineering, especially. So, as we're taking the existing structures, we need to assess the reliability of these structures in order to see if we can reuse or to. If not, we can adopt the demolition solution, or of course, in the end, to have the renewal aspect also. Sorry, the reconstruction and then recycling. I think I will pass to the. Sorry, I think it's a problem. I will put it the PDF. This is better. Sorry for interrupt. Confidential? No, it's not a confidential, but it was yeah. You go here and it will go to the system. Perfect. Thank you. Okay, so we are here. Okay. Oh, so as I mentioned, sorry for interrupting. As I mentioned, we need to consider this aspect of sustainability. So we need to assess the structures in order to see if they are reliable, and we need to have an approach given by, we'll see immediately, by fracture mechanics. So we need to do an engineering critical assessment of the existing structures. And we need to find an algorithm that we can do this with the existing structures. First, and secondly, why to not consider from the designing phase some kind of, why not, possible implication of the possible discovered flaws in the future if we have a visual inspection of the structure. We'll see why I'm considering also this aspect. So we need to assess this. So some example of of structures that have failed due to the problem of lack of inspection, of corrosion especially. So some examples here, it was not working the Jeep version. So we have an example of a Minneapolis bridge over the river Mississippi, 2007, August, 12th of August, the bridge collapsed. The main principal cause was the poor maintenance and the problem of structural integrity of the support of the piers. So as we can see, there are some indication of possible causes. The joints were under designed. Another example, Nanfango Ao Bridge from Taiwan, 140 meter span bridge. Again, lack of let's say maintenance, lack of inspection. The tension rods were corroded and the bridge collapsed. We are talking about a 20-year bridge in 2019. It happened in 2019, so it was a 20-year-old bridge. And another example of some wind farms, wind turbines from Germany, 2017, again collapsed due to the crack and the buckling of the entire structure. So we can see that we are having a lot of low cycle and high cycle fatigue structures that are damaged due to the problem that's bad maintenance, especially, and lack of inspection, and this leads to the collapse. So Peter Oem, a professor from Dresden University, made some kind of let's say report of damages of structures, and he documented over 400 cases. In the end, he reached to let's say some kind of conclusion that fatigue it is the third in place from causing the damage, the collapsing of the structure. As one can see, in case of bridges, is the first in place to be the damage cause of the structure. So bridges, I will give also some example about these structures. So we will need to think to a solution, very simple to be applied by civil engineers. Civil engineers are not mechanical engineers. They need to have some kind of, let's say, standard, the normative. We will need to have an algorithm for them to use in order to assess and then to make a decision upon a structure. This slide is very concluded because in a way it some kind of you can see our approach as a civil engineering. We are not having as a mechanical engineering applications, we are not having the defect as input data. So we are discovering the defects when we are assessing the structure, when we are visualizing. So we are going to have a visual inspection. So defect afterwards it can be revealed, and of course it's a problem because you have to take time to assess it and then to see the implication of that defect. So maybe a different approach, an approach that coming from also a sustainability development, in order to have this defect as a first, let's say, input for the structure itself. As we can see, discussing with Professor Beji from Wrocław University, yeah, indeed, we do have some standards. As we can see, we do have Eurocode 3 and 2 parts, fatigue and material toughness. But as Professor Filippo Berto told, this moment, there are maybe over conservative some, and some of them of these provisions are not enough for us as the civil engineering to use. So we need to apply, and we can apply this immediately, this engineer critical assessment procedure, which can be done during designing or during fabrication, or afterwards, as I said, during operation in service after visual inspection, maybe when a defect can be seen. So we can adopt the repairing procedure as over conservative, or we can consider this approach as engineering critical assessment applied in the civil engineering application. So Of course, in the end, we can conclude that the structure is safe, or it can be inspected, and then it can be considered safe if other cracks appear, or the crack will have extended, or I don't know, maybe other defect appear. Or repairing is mandatory. That means is needed to intervene. What we need, what are the input data? So we need the structural, the stress in the structural moment. We need the material properties, tensile resistance. We need the fracture toughness, of course, and we need the geometry of the floor. As the phases, we will have in the load range, we will have the applying the fractional mechanical, determining the fractional mechanical properties, and we will need to somehow categorize the floor. We will see immediately, determining the crack limit. If we go further with the fatigue, then we need to see the Paris crack growth power, and in the end, applying several cycles in order to crack the expand. I will show two cases. In first, historical steel riveted bridge. I will emphasize that in Romania there are more than there are several bridges which are more than 100 years old. They can be considered witnesses of the past because, of course, we need to present them as why not structure that passed through time. And I will present some phases of this, let's say, assessment. First, we will need to have the structural analysis of the existing bridge, then to have, we will see a retrofitting proposal, again, sustainability approach. Engineering critical assessment considering the most common possible discovered flow, and the fatigue assessment. As mentioned before, as civil engineering, we like things simple as it can, and to have the provisions for and the standards in order to address to a problem and to have a solution. So when you are having an existing bridge, you need to address, let's say, four phases, more or less. So we need to have a general checking of the fatigue, which is very common and very over-conservative, let's say, procedure with the relation, dealing with the stress, of course, and if this passes, okay, the bridge is okay. We will need to have the second, if not this, if over-conservative is not checked. Another procedure is to have the damage accumulation principle, found in Langer-Miner rule. And then, if not, also we'll need to apply fracture mechanic principle. But again, what is about this with the bridges situation in Romania? So we need to understand first that Romania was one of the first, let's say, European country where the steel industry produced in the 18th century. We need to emphasize also that the bridges were riveted at that time in 18th century. And if in the end of the 19th century, we had over around 2,000 tons. In the beginning of the 19th century, we had almost 4,000 tons of steel bridges were produced in Romania, because part of Romania also was from the Hungarian Empire. I will underline that Karl Madersbach was also an engineer that designed very nice bridges in the western part of Romania, in Timișoara region, Lugoj also. You can see some of his achievements and some of existing bridges that are also in operation in these days. These are from the western part. I will talk about very just one slide about Săvârșeni, the fifth in row, the Săvârșeni bridge of the Mureș River. This is a bridge. It was consolidated in 2009, and in 2010 this project obtained a prize from European Society for Construction and Steelwork. So it is very nice and let's say good project for Professor Bocila, Timișoara University, Polytechnic Timișoara University. So From the point of view of the bridges that are nearby Brasov in Transylvania region, I chose 4 of these bridges. We assess all these bridges and we try to adopt solutions for, let's say, retrofitting, we'll see immediately, and to see the actual situation to assess by means of this algorithm that I will show immediately. One of the bridges is Haitamare Bridge. Very short, I will not have time to present the geometry, 27 meters span. It's not a long span bridge. Some of the details, compound cross sections, also for the deck. The degradation were high, let's say, because of the corrosion and the infiltration coming up from the deck, the water infiltration. So we need to assess the if the bridge is workable, has the ability to sustain the loads. And we've done finite element modeling analysis, and in the end, we propose also a solution for retrofitting. Why not? Because it was a sustainable solution. So, instead of demolishing the bridge, we discussed with the local authorities to have it retrofitted. So we propose a solution to cut the bridge in two, as one can see here, and to put in the place a new beam. It's a girder, a box girder, which will sustain part of the loading. I should emphasize that the new bridge was designed for new Eurocode loading. So of course, to be adapted to the new mobile loading. Some of the views from the structural analysis, and in the end, the stresses from the finite element modeling, and we did apply the engineering critical assessments in order to see the implication of the possible discovered flaw. We tried to have the classification of these flaws according to British standard 7910, and in the end we applied syntax procedure failure assessment diagrams. Of course, just a few things about failure assessment diagrams. So we need to address the fracture toughness and of course with the specific tension from the LR and PL axis. So in the end, introducing the types of flaw, different types of flaw. These are what the types of flaw assessed: the thickness flaw, surface flaw, long surface, and buried flaw. These are the possible location of these flaws in the main truss, in the deck, right nearby the rivet also, and the results. This is the tabular form, but I will here can be seen the failure assessment diagrams more in depth. So we, as one can see, we can in this way investigate, maybe in a conservative way, the implication of the existing flaws. So the flaws that's the points that are outside the assessment line are not in can of course lead to let's say a problem in that element. So several cases were assessed. These are the results, and in the end, we need to assess the structure in order to see if the structure is reliable, considering the fatigue loading. So we need to establish, of course, a spectrum for loading, and applying Weibull distribution. In the end, we assess 5 types of flaws. Flaws that, in the end, are shown here as the implication of each flaw, the crack growth, the flow dimension of for each type of flaw, and the number of blocks, which means number of years. So we can see that, for example, a long surface flow, which of course it's normal to have 5.36 years, but we can see also the buried flow that is it's problematic. So here, in this way, we can assess very well the reliability, let's say, of an existing structure. So just short conclusion for this part. Engineering technical assessment was applied. New life for an existing bridge. That's very important. Very shortly, because I think I'm out of time already. Sorry. Antenna towers, another project that were done. Both projects again were done in collaboration with the Innovation Center with Professor Segmarko. Also, we tried to investigate the implication of the wind loading to existing monopole types, antenna towers for communication, especially. There were a large number of towers that were designed to be erected, to be manufactured for a company in Romania. So a large number, meaning 15 pieces. Considering the height, 40 meters, we need to investigate what are the possible implications of the discovered flaws in this structure. So again, the same procedure was applied. In this way, it was much more simple because we had a new structure and we could foresee what are the weakest points. So of course, the weakest points at the joints, at the base, and at the where the segments were connected. And in the end, for each model were determined, first of all, the maximum stresses. This is the nice images from the final modeling. Usually these images are capturing the audience. And in the end, we need to assess the wind load because we need to have the fatigue loading. So we need to have the nominal stress ranges. This came from the National Institute of Meteorology and Hydrology, and from Romania, and we obtained the results. And in the end, we had this spectrum, which of course needed to be interpreted considering the delta sigma. So we need to have different structural analysis for different wind loads. And in the end, using Bayesian distribution, we ended up having the number of blocks and the stress ranges and the frequency of it. So in the end, just to skip to this, we will have the results. Again, very nice presented results where we can see the flow dimension and the number of years that the structure can be without problems, or where we are having the most critical defects. We can see here for thickness flow type, crack in the welding, for example, or edge flow type. We can see the implication, the in-service lifetime is 5 years. Of course, these are conservative results, but again, we civil engineering we do like conservative results because we must rely on something. Of course, we do not like over, but we like conservative. So some of the conclusion, engineer critical assessment can be applied to determine the number of years until failure. We need to emphasize also the importance of this, considering the risk and the risk control. But nonetheless, we need to emphasize also the sustainability approach, proposal of strengthening if it's possible, and in the case of, if it's possible, also the retrofitting. So thank you for your attention. Sorry for giving you so much. This future research, I forgot to mention, Professor Sedmak and collaborator from Roki Institute from New Delhi, who will want to